All right, let's get started here. We're going to be working with these distributions. So without further ado, let's go ahead and do that. So I want to begin with the template, and I'm just going to go over this briefly. And this is what we're going to be using today. I like people to come up with their own study methods and whatnot, but I bring this up now because if you're still struggling keeping everything straight, I think this will get things straightened out. Now, here's one part of the flow chart for exam number 2. Another branch is going out to confidence intervals, which you'll be working on later this week, or maybe you've already got to that. And then later on down the road, also do hypothesis tests. All very different from each other, but how do you know you're going to be doing this sort of work on exam number 2? Well, they're asking you to find a probability, say, of one randomly selected being in the interval, or probability the sample mean will be in an interval, or sample proportion if you've gotten an 8.2. Or they might want you to find an interval that contains a proportion of the population. Your next question will be, what type of data is it? So it wasn't until you get to chapter 8.2 this came up. But from 8.2 on through the rest of this term, you've got to always ask yourself, what type of data do you have? Is it this numerical quantitative data that you can do meaningful math with? And by that I mean you can calculate averages. Or is it just names and labels? And which is categorical with just 2 categories, is also known as binary. But these are the 2 types of data that we deal with in this class. Now, if it's quantitative, you got one last thing to figure out. Is it a population distribution or a sampling distribution? And that can be answered by asking this simple question here. Now, all of these, and if it's binary, you know it's the sampling distribution for the sample proportion. But all 3 of those can be standardized into the standard normal distribution. Now that you know which distribution you have, then you go to the next page, which summarizes what you need to know. Well, you first learn about the population distribution. That's pretty straightforward. Shape, center, and spread's just given to you. You don't have to figure any of that out. But when you get to sampling distributions, you got to figure out if the shape is normal. Fortunately, it's not very complicated. You just have to determine either your sample size was at least 30 or more, or you're sampling from a normal population. And also, you have to wrap your head around what a sampling distribution is. So it's the distribution for all the possible sample means you could ever possibly get from repeated sampling. We actually know what will happen in the long run with repeated sampling. We know the shape, the center, and the spread. Follows that formula. And of course, this distribution could be standardized into the standard normal just by turning every sample mean into a z-score. Just like we could turn every data value into a z-score, this could be standardized into here, and so can the sampling distribution. And then, of course, when you got to chapter 8.2, you're dealing with binary data, and yet all those sample proportions that you get from repeated sampling will take on a pattern. And it too will take a normal distribution if the sample size is large enough to meet this little test. And all those sample proportions cluster around the population proportion they're estimating. And the spread of this follows this crazy formula. And of course, every one of those sample proportions can be turned into a z-score, and this could be turned into a sampling distribution. Okay, but this reminds you how to figure out the shape, center, and spread. Then you can go to the 3rd page. Now, this is the page that'd be worth making extra copies of, and you just fill it in as you work on each problem. And what this does is it reminds you of what questions you need to ask yourself, and you know exactly what to do. And it reminds you to run all the important concepts through your head. The idea is to keep using this on all your exercises until you don't need it anymore because you've learned the material. But it certainly helps you to get to that point. Because, it's the first part. Oh, we answered these questions already on the flow chart, didn't we? And then the all-important question, so you know which function you're going to use. Then you got a nice, convenient sketch to fill in, which helps you immensely. And then these questions you ask yourself. And then you know you've covered all the bases. All right, so before we get into one of those, we want to hit on some basic concepts. Hopefully you got these down now, but we just want to make sure that you're very clear on that you're working on the population distribution if one is being randomly selected. And you want to know the probability that one randomly selected is an interval. Okay, so that's a population distribution because one was randomly sampled. You can go to your little flow chart and that leads you right to this. And so here's the three things they give you, and this was the typical work you did a week ago, last week, for getting that probability. But then you got to chapter 8.1, and the thing was you weren't randomly selecting one, but more than one, because you're selecting a random sample, which is going to be more than one. And they want to know the probability that the sample mean from that random sample is going to be an interval. So you can see a very big difference between the population distribution. So that second sheet in that template would remind you that 16 is a small sample size. Yeah, but it's sampling from a normal population, so you're okay. And here's the center. The spread follows this formula. So you know the standard error. Each of those tick marks is 1.25. Now here's what's important. Now standard deviation tells you the standard or typical distance a data value deviates from the mean. But over here, this tells you the typical distance the sample mean deviates from the population mean. Oh, get that distinction. And we're going over here, so the big difference is the spread. So when you put in the standard error, you get a very different answer. And here's your interpretations. So you want to be able to be comfortable with this. That there's a 0.26% probability that the sample mean is less than 12.50. And it's a small probability, so that's an unusual event. Whereas this is the probability of one randomly selected being less than 12.50. That's 24.20%. That's not unusual. And of course, also be able to state it as proportion. So over here, we're saying this is the proportion of all the possible sample means we could ever possibly get. That will be less than 12.50. Very small proportion indeed. Now, let's go over this next page. Now, when you see, and this is going to start happening when you get into confidence intervals, you're going to see the standard normal distribution. It's important that you know this does not represent the population distribution. It's the standardized sampling distribution. Because for your sample mean, every sample mean can be turned into a z-score. This is the center and spread for your sampling distribution. So this sampling distribution turns into this. So when you see this, when they're explaining how confidence intervals work, know that this represents the distribution of all the sample means, or sample proportions if it's that sampling distribution. All right, so let's go ahead and let's try out that template on assortment of problems here. I'm going to scoot this over here, make it a little smaller so that way I can also look at the template. There it is. We'll scoot this over here. All right, so the lengths of all fish in Lake Erie are normally distributed with a population mean of 8.50 inches and a population standard deviation 1.50 inches. Now, what's the probability of one randomly selected fish being more than 9 inches? Let's go to our little flow chart here. What's the probability? So you know This is what they're asking for. And we're measuring length, so that's quantitative. Last question. Was one or more than one randomly selected? One. So that's how you know it's a population distribution. Pretty straightforward stuff then. Now it's just what's given. So let's just go through this little process here and fill this little thing out. So let me get my little annotation tool here. And as we've answered over here, you're just saying, well, let's see now. I did quantitative. One was randomly sampled. That's how I know it's a population distribution. What were you given? What were you asked to find? Well, I'm looking over here, and they gave me this interval, more than 9 inches. So I was given an interval, and they want me to find a probability, and that's an area under the curve. So they gave me an interval, asked me to find an area under the curve. Who does that? Normal CDF. Okay, so I know which distribution I'm working with. I know what function I'm going to use. So the shape is normal because, well, for this, it was given. And of course, that's only with a population distribution is that true. And then let's jot down our center, which was the population mean at 8.50. And this spread was the population standard deviation, which is 1.50. Okay. Now, let's put an X here. So it's a distribution of all the data values. It's quite helpful. So if this is 8.50, each is 1/2. So let's see, that'd be 9, 10, 1150, 12, 13. See, 8, this would be 7. See, 6, 5.5. And 4. 5.5. All right, and then they want to know being more than 9 inches. Well, 8.5, 9, 9.5. So you can figure it's about a third of the way over here. But of course, sometimes that's not so obvious. So what you can always do, just turn it into a z-score, and then it'll be easy to locate on there. And you'll have it accurately located. And when you accurately locate, then your sketch of your area is going to truly represent what your answer is. That's why it's nice to use a ready-made, accurate, perfectly symmetrical curve like this template provides you. So let's see, we're going to take that 9, subtract the center, 8.50, and divide that by the standard deviation, 1.50. And then I'll get over to my calculator here and do our little arithmetic. So we got 9 minus 8.5 and divide that by 1.5. Yep, just as we thought, that's 1/3 of a standard deviation above the mean. So I'll go ahead and accurately put that in. So let's see here. That looks like about 1/3 to me. So we got that. Now, which way do we shade in? Well, what did they say to do? Oh, now I'm covering up my little paper here. More than. So we got to shade in to the right. So let's go ahead and do that. So you can see it's a pretty big area. So it's not going to be an unusual event. It's going to be less than 50% and definitely more than 5%. We can definitely narrow down that much. All right, so we've got that. Now, use your sketch to help you write out what you're looking for in the inequality notation. Hey, that's a good idea. So I'm going to do that. Let's go over here, and I'll do a little arrow. So let's see now. So that right there, that's my 9. So I'll go ahead and write that in. So that's where my 9 is. And see where I have it shaded on the right? That's all my X data values. So they're shaded on the right, so I put my X over on the right. Now you compare the two, whoever's farther to the right is the larger, so it gets the big end of the inequality, 9 smaller, so it gets a small pinched end. Put parentheses around that, capital P in front, and there's the shorthand notation for the probability of one randomly selected data value being greater than 9 inches. Now, let's go ahead and show our work. And you'd want to do this on exam 2. Always show the function you use in the inputs, because that's how you get partial credit if anything were to go awry on you. And also what I'm showing you, this is all the sort of stuff you should do on a problem when you're doing the online homework. Do all of this writing it out first before you enter in your answer, because that's what's preparing you for exam 2. Now, our sketch has everything I need. So we're going to put in the lower bound, upper bound, nice little template here. So the lower bound's always on the left side, the upper bound's always on the right side. So our lower bound is the 9. Upper bound is anything way larger than 13. See, when you put in the numbers in, you can just see, well, 20 would be large enough here. Want to do something larger? Go ahead and do it. But just go way off to the right. And of course, my center and spread's right here. It's very convenient. And 1.50. So let's suppose you just accidentally punch one of these numbers in wrong. If you didn't show this work, you would lose all the points. But if you showed all this work and I could see that, well, they knew the right function, they had this right, and this right, or maybe you had one number wrong, you're going to get partial credit for what you did correctly. But you can't get it if you're not showing your work. So please, please show your work. So let's finish the job here. Second vars 2. And put in our 9, something big for the upper bound, population mean, and our population standard deviation. And I should double check, make sure I didn't punch something in wrong. Looks good. And there's our answer. So let's put that in. So it's 36.94%. And if you, to really reinforce that, you can say to yourself, aha, so that, or you say, yeah, that looks pretty reasonable. No, it's less than 50%, and it's not unusual, way more than 5%. Now, then, of course, you're asked to state the results in context. And so let's go back here so you can see the context. We're talking about the fish in Lake Larry. So you'd say 30. Oh, let's see. I want to say it's a probability. So the probability. Oh, and before I do that, let me write it out like this. That way you can just point to the notation as I am saying it. So this is equal to the 36.94%. So the probability of one randomly selected fish from Lake Larry being longer than, as we're measuring the lengths, longer than 9 inches is 36.94%. And that's not unusual. That's way more than 5%. Now, is this unusual event? So I'll say no. And then staying as proportion, 36.94% of all fish in Lake Larry are larger than 9 inches. Okay, so that's all the work you do. Now let me go ahead and clear all of this. And if we go over here, you can see the work looking much neater and tidier. Oh, and plus you can see in writing what I said. But this is what I did. I just didn't look as neat as I'm scribbling on my little tablet here. You want to show off. See, on this time here, I did the 1E99. So if you want to do 1 times 10, raise the 99th power, you can. You don't have to do that, though. That's what I want to emphasize is as long as you do something way off to the right. Okay, let's look at another one. Now let's go back up to our little flow chart. The length of all fish in Lake Larry. Hey, this is the same population. Yeah, but it's a different question. Because now what we want to know, if 16 of these fish are randomly selected, what's the probability that the sample mean will be more than 9 inches? Well, that's a very different question. Because now we're doing a probability, it's quantitative, but more than one is being sampled. We got 16 being sampled now. Where can I find the blank template for distributions? You should have gotten an email from me this morning when I sent out the reminder. But there's another place you can get it too. So let me just show you where that is. So when you go into our little website, my Stat Lab, click on External Links and click on Files from Live Lectures. And this is session 5. You click there, and there's the template. So you can also get the template right here. Plus these other documents we're going to look at, so you'll be able to access that. All right, so let's see here. So we know it's a sampling distribution for the sample mean, so you refresh your memory. Oh, let's see. Oh, I had a small sample. Oh dear, oh wait a minute. I'm sampling from a normal population, so we're okay. The center is going to be the population mean 8.50, but I'm going to have to use this little formula to find the spread of my sampling distribution. All right, so let's move on. We did all the preliminary stuff. Now we can go ahead and fill out our little template. So we'll go ahead and do that. It was quantitative data, so we'll just put a little check there. And more than one. Well, if it's quantitative, more than one's being randomly sampled, that's how we know it's a sampling distribution for the sample mean. Now, we were given an interval, which was the more than 9 inches, and we're asked to find a probability, which is an area under the curve. Well, if that's the situation, then this is a job for normal CDF. Shape is normal because we're sampling from a normal population. The answer is not, because they told us it was normal. They didn't tell us the sampling distribution was normal. Now, did they? Well, isn't that what I meant? Well, that's what you said. So we're sampling. So it'd be more clear to say it this way. Because if you're trying to teach this to someone, I don't want you to confuse that someone by saying it unclearly. And the center is equal to the population mean, because all those sample means cluster around this population mean, 8.50. But how closely do they cluster? Well, amazingly, it follows this formula. The spread of the population you're sampling from, divide by the square root of the sample size. It's kind of amazing. That's what sample means do. And so we got our population standard deviation of 1.50, and we get a sample size of 16. So let's see what that standard error is equal to. So 1.50 divided by the square root of 16. And that means that typically a sample mean is only going to be off by 0.375 of an inch when it's estimating the population. Typically, that's how close a sample mean will be to the population mean it's estimating. Wow, that's pretty close. Well, let's get this written down. So this is equal to 0.375, and let's emphasize that's an inch, 0.375 an inch. It's not a percentage, okay? Just because something looks like it could be a percentage doesn't mean it is. It's just that these sample means are clustering in so closely, it's less than an inch. So let's see, we got 8.50 here. Now, to really emphasize to ourselves just how closely they're clustering in, let's go ahead and put these numbers in. So I'm going to do it this way. I didn't hit the 8.50. I'm going to subtract one standard error of 0.375. I like doing it this way because then I can press second and enter and just change the minus to a plus. And this way I'm looking at the interval that contains the middle 68% of all the sample means we could ever possibly get. I'm going, wow, you mean 68% of all the sample means are going to be clustered this closely from 8.125 of an inch to 8.875. 68%, that's essentially 2/3 of all the sample means are going to be clustered that closely, within 0.375 of an inch. Wow, they cluster in close. So the sample means can really do a good job. And this is only a sample size of 16. It's not even a large sample. Now let's go ahead and go two standard errors. And all I have to do is press second enter. Let me try that again. Second enter. Change that +1 to a subtract 2. Press second enter. Change the subtract to plus. So now we know the middle 95% of all the sample means. So this is essentially all the samples that are reasonably close. They're all within two standard errors. Is between these two values. 7.75 of an inch. In other words, 7 3/4 of an inch to 9 1/4 of an inch. Boy, they're clustered in close. Now let's just finish the job here. Second enter. Make that a subtract 3. Second enter. And make that minus plus. So pretty much all of the sample means are going to be between these two values. And so we got 7.375 and 9.625. Wow, those don't stray too far away. Now, but where is 9 inches now? Because that's what they want to know. Well, it's somewhere between here and here. Well, let's turn it into a z-score. So it'll be easier to locate that way. So what I got to do, I got to take my 9, my sample mean, which is 9, subtract the center. Of course, you got your center right here, 8.50. And you divide by the spread of the sampling distribution. So use your spread here, the 0.375. Now let's calculate. Let's see how far away that is. So I got 9. Oh, I want to do a parenthesis there. There we go. 9 minus 8.5. And divide that by the 0.375. And it's 1 1/3. Boy, when we in our population distribution, 9 was just 1/3. But when the sample means clustered so closely, we're 1 1/3. So let's go ahead and put that in. So let's see, that looks like about 1 1/3. So I'll draw a line there. And then we'll shade in to the right because they want to know that are more than 9 inches. So this is a much smaller area than what we were working with, the population distribution. Now let's go ahead and let's use my little sketch here to help me make my notation. So going up this way right here, that's where my 9 is. So I'll put my 9 right there. And all my X bars are off on the right, so I'll put an X bar over here on the right. Compare these two, whoever's farther to the right gets the big end, whoever's on the left gets the pinch small end. So that's what your notation would look like. The probability of the sample mean being greater than 9. Now let's show our function we're going to use, like we said, is going to be normal CDF. And then I'm going to use my sketch because all the numbers I need to put in here are right here in my sketch. 9 is the lower bound. Hey, this time I'll do the 1E99. I didn't do it last time. And then put in your center of 8.50. And because you did all this work, you're going to put in the correct spread, the standard error, which is the 0.375. There, you got all your work shown. Now all we got to do is punch it in. So second bar is 2 and 9, a comma, and then I'll punch in a 1. Now to get that E, you got to press the second key and the comma key. You get that funny, it's a small little E, 9. And that's how you enter in scientific notation. That's 1 times 10 raised to the 99th power. Let's see, put in our center. And 0.375. Now, by the way, if you accidentally put in the population standard deviation here, you'd be getting the same answer we had on the last problem, which would be wrong for this one. So that's our probability. You say, yeah, that seems reasonable because this is 2.5 here. We're moving over this way. So seems reasonable that that would be an answer for this. So it will be 9.12%. Is this an unusual event? No, because the probability is greater than 5%. Now, before I show you the nice tidy version, but here's what I want you to do. That's 9.12%. Might even impress upon yourself that that area right there is the 9.12%. So the probability that the sample mean will be greater than 9 inches is 9.12%, not unusual. And 9.12% of all the possible sample means you could ever possibly get from resampling are going to be greater than 9 inches. All right, so let's clear that. And then we'll go down, we'll scroll down. Whoops, didn't mean to. Forgot to turn off my annotation tool. So there you go, a nice tidy version, all typed up. All right, now let's go try. Okay, now this is working with the standard normal distribution, and this is a notation that you're going to see coming up when you start working with the confidence intervals. And it's critical you know this because what that z-score is called is the critical value. So, well, first of all, notice that when you see the z, you just automatically know it's the standard normal distribution. In fact, we can just get our little annotation tool because right here, you can just check right here. It's the standard normal distribution because I can see the z. Oh, that's pretty straightforward. We'll put our little z in there. Oh, I guess I won't do it there. I will do it over here. And what we want is the z-score where the area in the right tail is 0.025, which is 2.5%. So I'll just go over here and this one's so simple. I'll go ahead and use the template anyways. I'm going to clear that just so I can move this up like that. Yeah, that'll work. All right, so we're going to start marking away here. And now you say, is quantity, well, see the thing with the z distribution, it could be either one of those because it's been standardized, so it really doesn't apply. Same thing here. You just kind of jump down here for this one, It's the standard normal. It could represent any one of those. Now, so let's make a little picture of this. Let's put a Z there. And so that little subscript is the area that's in the right tail. So let's say you start at the center and the area to the right is 50% in the right tail. Well, this is much smaller than that. So you just know you need to go off to the right. You might already know that 2.5% is about here, but you don't have to know that. You can just be eyeballing it. But just clearly label that area right there is 0.025. I'll put a 0 in front of that O. And that this right here is the z-score where the area in the right tail is 0.025. Now, once you have that, you realize that, oh, the center is 0, spread is 1 because it's the standard normal. Shape is normal because it's the standard normal. Part of the name that it's normal. Distribution. And so we see that, oh, we've been given an area under the curve and we're asked to find the interval. We know the upper bound's positive infinity, but we want to know the lower bound. So essentially we're finding an interval. So this is a job for inverse norm. Okay, so we're clear on that. Well, what does inverse norm need to know? Well, we can find that value if we use inverse norm. But inverse norm, as we can see from the template, needs the area to the left, and I just got the area to the right. Well, I guess it got a little calculating to do. Now, I certainly hope it's clear to you, since the area under the curve represents the proportion of the population or distribution, that area would have to add up to 100%. And what does 100% look like in decimal format? 1.00. So from 1, subtract the 0.025. And you know what would have to be on the left, because this plus this would have to add up to 1. So I know the area right to the left there is the 0.975. Since that's the areas to the left, that tells you the percentile rank for this z-score. So it's at the 97.5th percentile, which is the area to the left, 0.975. And of course, 0 and 1 is the center and spread. Now we can go find that z-score. So second vars 3, whoops, let me try that again. 0.975, comma 0, comma 1. And that's the z-score. And if I'm rounding to 4 decimal places, it's 1.9600. Now what this is telling you is that if I go 1.9600 standard deviations above the mean, only 2.5% of the distribution will be larger than it. And this is true for any normal distribution, whether it's a population distribution or a sampling distribution. Of course, if it's a sampling distribution, I'd be saying 1.9600 standard errors instead of deviations. And is this an unusual event? Well, here, let's put this in our probability inequality notation, which is something I encourage you to do to make sure you're super clear on what your answer is. So notice that this value right here, that z-score is 1.9600. And all the z's are over here on the right, so I'll put z over on the right. So it gets the big end. So there's probability notation, and that's equal to the 0.025. So this just gets clear in your head that you know which number is the area under the curve and which number is a point on the number line. That inverse norm is giving you either a lower bound or an upper bound to an interval. It's always a point on the number line. All right. So hopefully you'll be getting comfortable with that. Now you knew that if you went approximately 2 standard deviations above and below, that you have 2.5% in this tail and 2.5% there. But now you know to a little more accuracy, it was approximately 2 standard deviations. It's a little more accurate to say 1.9600. Or if you want to be even more accurate, you can use this right here. Okay. But when we're doing our intermediate calculations, 4 decimal places is usually pretty adequate for statistics. So let's clear all those scribblings. And here you can see the nice and tidy one. And also notice the interpretations. For any normal distribution, 2.5% of that distribution will be more than 1.96 standard deviations or standard errors above the center. Standard errors if we're talking about a sampling distribution. And you know what? It will be a sampling distribution as you go through the rest of this course. The other one is, well, there's a 2.5% probability that one randomly selected from any normal distribution will be more than 1.96 standard deviations above the center. Or if we were talking about one randomly selected sample mean being randomly selected and being more than 1.96 standard errors above the center. All right. Now, so that takes care of that. Now let's go over to, let's talk about binary data, because all we've been talking about over and over again is the quantitative data. So let's make that little switch, because, when we get to the statistical techniques, we're just as likely to be working with the numerical data as with the numerical quantitative data as we are with the binary or categorical data. Now, what we were just doing when we were finding that critical value, this will come up and you're working with the confidence intervals. I'll say, hey, we want you to find the middle, how many standard errors do you have to go above and below the center to contain the middle 92% of all the sample means? Well, that sampling distribution has been standardized here. So this will tell you how many standard errors you have to go. So it's telling you the distance in standard errors. So you'd have to figure out what's in each tail. So subtract. So you'd go over here, take the entire area under the curve. Let's see, there we go. I had to wake it up. Take the entire area under the curve, subtract whatever that middle percentage is. That's what the 2 tails add up, so divide that by 2, and you know what's in each tail. We got 4% in each tail. So that means the critical value, the z-score that will tell you how many standard errors you have to go above and below the center to contain the middle 92% of all the sample means. Yeah, there you go. So I just need to find that z-score. I'd have to find the area all the way to the left, which would be the 92% plus the 4%, which is 96%. So now you could go over here, go to inverse norm. So it's at the 96th percentile. So let's see what z-score is at the 96th percentile. Well, inverse will tell you. I have to go 1.7507 standard errors above and below the center to contain the middle 92%. Now you know. Now we can get into binary data. We divert a little bit, but that really applies to what you'll be working with this week with the confidence intervals. All right, so things are a little different here. The data is very different. And so when you're learning statistical methods, you got to know which data you're dealing with, or you're going to be using the wrong statistical method. And if you do that, your answer is wrong. So it's kind of a serious error when you make that. So now what I think will help you the most, this is what I always strongly recommend to students. But go to the lecture notes, go to chapter 8.2, and I would actually recommend printing out page 2 and page 3, because on those I have summarized for you side by side what you should probably be reviewing every day. Not only every day, but more than once a day, maybe 2-3 times a day, till it starts to sink in. The similarities and differences between quantitative data and this categorical binary data, side by side. Some things are similar, but a lot of things are different, and you just got to get it super clear in your head. Think of this as that last hurdle of big concepts you need to wrap your head around for this course. Because after you get through chapter 8.2 and you've really mastered it, the rest of the term, which is the whole second half, is much easier. But that second half won't make sense unless you really understand these sampling distributions and you're super clear on the similarities and differences between your two types of data. So that's why these 2 pages are so valuable, and to keep and pin them up somewhere that you're going to walk by and think, oh, let me run it through my head one more time until I really get comfortable with this. There's some wild things that, with binary data, the population has no shape, center, spread. It's just a freaking bar chart. And yet, your sampling distribution is something entirely different from a population distribution. Because every time I take a random sample from there, I'll get a sample proportion. I find out what proportion of my sample is in the category of interest. And as you repeat that process over and over many, many times, patterns develop. And that's what a sampling distribution is, the pattern that develops from repeated sampling. Keep running that through your head. Play with that little Java applet that you have available to you in the learning modules to help you visualize the process. But this page really helps you get it visually. The first page, it's more verbal, it's more wordier, but you really need both. So, hope you'll take advantage of that, print those 2 pages, and keep reviewing them. Now, that being the case, so you'll be comfortable, and this is your little template reminded you of this. This is how you knew the shape was normal. This is the center. Remember, P is your population proportion. So what is a population proportion? Okay, so you've got a population of categorical data. It's just names or labels. And there's only 2 different names because it's binary. There's just 2 categories. And you're dying to know, well, what proportion of the whole population is in one of those particular categories that you're interested in? That's your population proportion. And so you'll see that all you need to know to figure out the shape, center, and spread is what is that population proportion and the sample size. You say, well, yeah, sure enough, I could find out everything else. And so that's what we'll be doing. So questions you ask yourself: what type of data is this? How many are randomly sampled? One, more than one. In other words, the little flowchart questions. And so, hey, let's just move this over here. Why don't we just use our little template on this? Well, we'll scoot this over here, and then we'll get our template. Because if we ever need a template, it would be with a problem like this. So let's scoot on up here. All right, so what we're looking at, let's go over here. So we went to class and the teacher was handing out Reese's Pieces. You got 75 pieces of this candy, and there's a random sample of them. But let's suppose we know everything we really need to know about this population of binary data. We actually already know what proportion of all Reese's Pieces are orange, 40%, and our sample size is 75. So we go over here. Oh, and eventually what they're going to be asking us, it's supposed to do that. Orange, I know we have that. So, we're getting all of that. And let's see if we can see if they ask a questions. Let's suppose that 75 Reese's Pieces that you received, only 21 of them were orange. Okay, so 21 out of 75 were orange. So what would that be? Let me wake up my calculator. There, that usually does it. Now I've forgotten what it was. It's 21 out of 75. All right. I had to refresh my memory on that. 21 divided by 75 is the proportion of my sample that were orange. 28%. So 28% are orange. And we want to know, is that unusual? All right, so let's go over here. Now, what type of data is this? Well, they ask the probability because once we know the probability, we'll know if it's unusual. It's binary, so we know it's a sampling distribution for the sample proportion. And this reminds us of the formula we need to use, in particular, the one for the standard error. I mean, center's easy. We know what that is. And of course, we'll do this to see if the sample size is large enough. Now, don't say, wait, 75, that's larger than 30. Hey, don't do that because 30 being a large sample only applies over in the world of quantitative data. It's a whole different world here. For this to be a large sample, it has to pass this test. In fact, we could just go over here and you can see them doing the work here because we had our P, which was the 40%, and our sample size, which was 75. And if you go ahead and punch on your calculator, 75 times 0.4 times 1 minus 0.4 is 18. And that's larger than 10, so our sample size is large enough to ensure that our sampling distribution for the sample proportion will be normal. And so once we got that, let's go ahead and fill this in like we've done with the others. So it's binary data. More than one was sampled. In fact, 75 were. And it's a sampling distribution for the sample proportion. Our little flow chart told us that. And so that sample proportion we got, that's a point on the number line. Okay. So essentially, we were given an interval, asked to find the area under the curve, because we're going to want the area under the curve is going to tell us the probability, which will tell us whether that's unusual or not. So that's how I know we're going to be using normal CDF. Let's put a little p hat here, remind ourselves. Sampling distribution for the sample proportion. This is normal because n times p times 1 minus p. And whenever you do this, you should show your work. So let me set a good example. So n was the 75. And p was the 0.4, and then the 1 minus p, 1 minus 0.4. And when you punch that in your calculator, equals 18, which is greater than 10. So this way we're demonstrating we knew how to check it, and we checked it. Now the center is equal to the population proportion, which we know is 0.4. So that would be in the center here. Now the spread, that's that crazy formula. I'll go over here so I got room to do all of that. Now, of course, you don't have to memorize these formulas. It's be on your formula sheet. P times 1 minus P all over N. So that would be, I'm going to show you how to, best way to punch this in your calculator. 1 minus 0.4. All over N, which is 75. So when I punch this in my calculator, the easiest way to do it is first punch in what's under the radical sign and calculate that. And then I'm going to take the square root of that answer. Let me show you how I do that. See, there we are. All right, so I'm going to do my 0.4 left parenthesis 1 minus 0.4 right parenthesis, and then divide by the 75. So that's what's under the radical square root sign. Now I want to take the square root of that. Now sometimes it's the answer will be in scientific notation. You wouldn't want to punch it in. You don't need to. Just do this. First we'll get the square root symbol. Press the second key, x squared. Now to get your last answer, the best way to do it is press this second key here and this key to the left of enter. Puts an A and S, which stands for your last answer. So if it went off many, many decimal places, this will maintain all the accuracy. There. Wasn't that a lot easier doing it that way than trying to enter the thing all in one fell swoop? So that is our error, our standard error for this sampling distribution. Now, when I use this as an intermediate calculation, I'm going to want to go up 4 decimal places. So 0.0566 is what that would round off to. Okay. Now, when you're doing your rough sketch, you don't need to go out 4 decimal places. So for me, that would round off to 0.06. And of course, you'll be off a bit because I'm rounding off a bit here, but it won't be too bad. So what we could do is we could go ahead, go to our calculator, and I'll put in the 0.4, and we will subtract one of these standard errors. Now I'm going to put in 4 decimal places, but when I write it in, I'm just going to round to the second decimal place. 0.05. And let's see, that looks good. And then I'll press second enter. Change that to plus. So this is how closely those sample proportions are clustering around. Now, if you want to go right in 4 decimal places, that's fine. But, this is just a sketch. So I'm just going to do the 0.34 and 0.46. And then we'll go ahead and press second enter. Make that a subtract 2. Second enter, make that a plus, and let's write that in. So down here it's a 0 point, and I'll round off to 29. And up here we have a 0 point that rounds off to 5.1. And then we'll go ahead and finish the job. that in. So this would round off to 0.23 and this to 0.57. Okay. And of course, be a little more accurate if I went out 4, but this is just a sketch. Now, what we were looking at here was we want to know how unusual it would be to get 21 out of 75. And when we did that, 21 out of 75 was 28%. So 28% is somewhere between here and here. Let's turn it into a z-score. What do you say? That'll make it easier to locate. So to turn that into a z, so first of all, our p hat, let's just make a note of that. Our p hat is equal to 0.28 because that's 21 out of 75 that are orange. So the z-score for that, we would take the 0.28, subtract the center, which is the 0.4, and we divide by the spread, which is the 0.0566. So that'll make it easier for us to locate where it is under the curve. It's 2.12 standard errors below. That's just what we were thinking. We knew it was in between there, but now we have a much better idea just where it is. So that'd be 2 and just 1/10, so that's just a little bit more. Something like that. Now, if you want to know how unusual it is, which side do I have to shade in? This is an important concept. What unusual means is to be that far away from the center or farther away. That's how you tell how it's unusual. Since I'm off on the left, then I'd want to shade in the left side. So I know how unusual it is to be this far to the left or even farther away. So it's that little area there. Looks like less than 2.5%, unless I've rounded off too much here, but it's looking kind of small. So let's go ahead and I'll use my sketch here to help me with my little notation. So that point right there is the 0.28. And my p hats are to the left, so I'll put p hat to the left. The 0.28's farther to the right, so it gets the big end. So here's what the notation would look like, just like that. Oh, in fact, you can see on my little over here, where I went out the 4 decimal places, so it's not too bad. 0.23, 0.29. But we got the 28 there. Now let's go ahead and use our normal CDF to see what that probability is. So normal CDF. Now, so your lower bound is anything way off to the left there. Oh, I got a question here. So if we had an answer to the right of the center, we would shade the right. That is correct. So if we were over here on the right-hand side, we would draw a line there and shade into the right. So you're going away from the center. Let's get back over here. So anything way to the left. 0 would be far enough to the left. If you want to do -1e99, you could do that. But I'm going to do 0. But you can definitely go farther. But when I have a sketch, I have an infinite number of values that'll work just fine. And the upper bound is a 0.28. And the beauty of having your sketch is everything you need is right here. And you've got your center and spread right there. You don't have to go hunting for it anywhere. It's right there, easy to find. And do go out 4 decimal places so you don't have too much round off here. You can go more decimal places, but go out at least 4 like this. All right, so now we can punch that in. Now let's see, second vars 2, 0, 0.28, 0.4, and 0.0566. And if you want to go out more decimal places, you can certainly do that. Yeah, so we knew it was going to be a small probability. Definitely looked like it was less than 2.5%, and it's about 1.7%. So that looks very reasonable according to our sketch. So that's equal to 1.69, we'll say 1.7%. So that area right there, 1.7%. So is that small enough to be considered unusual? Yeah, because that's much less than 5%. It would be unusual to get a sample proportion that far below or farther below from the population proportion. Because if 40% of Reese's Pieces are orange and you only got 28%, why, you got an unusual sample. And think how upset you would be if you really loved the orange ones. And here you got so shortchanged. So only 1.7% of all the possible sample proportions you could ever possibly get from repeated sampling are going to be less than 0.28, 28%. All right. Now let me go ahead and clear that. So you can see the much neater, tidier one. And plus it's going out 4 decimal places. Oh, and here you can see I did the -1e99, so you can do that. So I like to do it one way as I do it by hand, and then you can see it shown this way too, just so you know they all work. Plus you can see it in writing there. Your 2 interpretations. Okay, well, that's the things you're going to be going over, and this is the most of the work, because if you really get this down through chapter 8.2, you're going to have a much, much easier time with everything that follows, starting with the confidence intervals. And I touched on some of the basic concepts that are going to come up with confidence intervals, but as long as we're here, let's mention a few things about it. Let's go ahead and put that. But really, your big focus, get those sampling distributions down. Those 2 pages I showed you from chapter 8.2 where you keep reviewing the similarities and differences between them, definitely do that every day. Because you don't want that tripping you up. So here you can see those practice exercises worked out. Now, after you finish chapter 8.2, what you need is some practice to see if you can recognize which type of problem is coming next, whether it's from chapter 7, chapter 8. In other words, you've used that template enough times, you know what questions to ask because you remember the flowchart questions, so you know exactly which type of problem it is, and then you can solve it. So this is an assortment of those. So you should work on those, doing your very, very best, and then check your work. So you know how to do it, right? After last week's presentation, You'll grab one of those and you will work on it and push yourself. Push till you get an answer, and don't give up too soon. And then after you've done your very, very best and you've got an answer, compare it with the answer here without looking at the solution. And if it's the same solution, then you can go ahead and look how it was done. But if it isn't, then you're going back to what you did and see if you can figure out what you did wrong. So this is a perfect opportunity if you want to try out that technique I showed you. The proven that it's been very effective in student learning. Now let's get back over here to the main menu and over here to the learning modules. And let's see here. Let's going to 14. Yeah, so 14 covered the sample proportion. So then when you get to 15, this is the one where you're kind of reviewing the two. Just getting a little more time to get it to sink in. Then when you get to 16, you're starting the second half of the term essentially. And you're getting into confidence intervals. And what you have here, you got the lecture notes, of course, but you also have the movies. So you got confidence intervals part 1, this movie, confidence intervals part 2, and part 3. So they're in small little parts, but you got the movies to learn the material in addition to the lecture notes. Okay? Well, that covers what I really want to get covered this time. And oh, there is something more I want to touch on, and then we'll be done. So if you think of any questions, we better start asking away because we're going to be done here pretty soon. Let's see, it's right here. This document. Was it this one? Yeah. Okay, so here's what you want to remember. So I recommend printing out and use a copy of, actually I should say page 3. Page 3 is what it should say because that was the one that you're filling out. Now, it's going to step you through all the important concepts and questions you need to ask yourself. So you're going to be really drilling in. You'll be applying the concepts. You know, that's what makes the concept questions much easier to remember if you're applying them. Oh, hold on. I got a question here. I assume we don't get the flow. No, you got to keep using that until you don't need it anymore. It's a valuable learning tool, but the idea is use it till you grow beyond it. Now let's see. So once you identify the type of distribution, then you got the summary to run that through your head. Once again, you're doing this over and over till it sinks in. During your intense study sessions that we talked about last week. And then filling in the template for distributions. And of course, I showed you where to access that. And then this is those practice problems I told you about. And so once again, you could be lots of opportunities here to be applying those metacognitive strategies I showed you last week. All right, well now I got it covered. So we'll see you next week.